Welcome to the Picture Language Seminar. It's a tremendous pleasure today to have Andrew Childs. Andrew is professor of computer science at the University of Maryland. He's a former student of Ed Farhi. He's an editor of CMP, director of NSF Quantum Challenge Institute at Maryland, and also co-director of the Center for Quantum Information and Computer Science. Today, Andrew's going to tell us about quantum divide and conquer. We're very much looking forward to your talk, Andrew. So you can share your screen.
Great, fantastic. Yeah, thanks, Arthur, for the opportunity to speak. There's the share button. There we go. Great. Does it look all right?
Terrific.
Great. Yeah, thank you. So, yeah, thanks for the opportunity to tell you about this work. If you have questions during the talk, please don't hesitate to just interrupt and ask. If we don't make it through everything, I'm happy to spend more time answering questions and maybe less time trying to go through all of the slides. So this work is on the topic in quantum query complexity, quantum algorithms, and it's joint work with some fantastic co-authors. So Raman Kothari, who was at Microsoft when we did this work, although he's now at Google. Some students at the University of Maryland, Matt Koachdik and Dao-Chen Wang, and Arthi Sundaram, who's still at Microsoft and actually formerly was a postdoc here at Quix. So you can find this work described in a preprint on the archive if you're interested in more details. This was also presented at QIP just a few weeks ago. So yeah. So what's the topic here? So we're interested in, kind of broadly speaking, understanding this question about the power of quantum computers, right? So what are the problems that we can solve fast with quantum computers that we don't think we can solve fast with classical computers? Or what are the kinds of computational speedups that we can get from trying to solve problems on quantum mechanical devices? And sort of the general picture is that if we do a computation that somehow takes advantage of the ability of having different paths of the computation that can interfere with each other constructively or destructively, then there are some problems for which we can find a solution much faster, quantum mechanically, than we would be able to using a classical computer. So as you probably know, there's a variety of kinds of quantum speedup that we can imagine. I mean, for some problems, we get basically no quantum speedup, but there are some problems for which we can really have exponential quantum speedup, or at least a super polynomial speedup over what we can do classically. Either over what we think we can do classically, what we know how to do with the best known algorithms, or in some cases, depending on sort of the model that we're working in, sometimes we can even prove that we can have an exponential quantum speedup. So, the best known example of a problem like this, where we think we have, something like an exponential speedup, is probably the factoring problem, from Shor's algorithm. But there are a bunch of other kinds of problems for which we have, we think we have exponential quantum speedup, or as I was saying, in some models, we can actually prove that we have exponential quantum speedup. There are other kinds of problems where, we have polynomial quantum speedup, and this is, perhaps, this is a less significant speedup, but there's a kind of, I would say, a broader variety of problems for which we can get these kinds of speedups. And I think it's interesting just to understand, kind of from a fundamental perspective, what are the problems, also for which we can get these polynomial speedups, and, exactly how much speedup can we get? So Grover's algorithm for unstructured search is probably the best known example of, a quantum algorithm that gets polynomial quantum speedup. There are lots and lots of other examples of problems for which we can get, speedups, something like quadratic speedups, or maybe a little bit less than quadratic, in some cases even a little bit more than quadratic, polynomial quantum speedups. So the stuff that I'm going to talk about today is in sort of this direction of finding problems where we can get some polynomial quantum speedup. Although, as I'll mention with an open question, later on, it's not clear that we couldn't have larger speedups, using this technique, and that's something that I think would be interesting to explore. Okay, so this is really kind of just the basic question that we would like to understand. What are the problems that we can solve significantly faster using quantum computers than classical ones? Okay, and so to understand this question, there's kind of a an obstacle, which is that we have sort of not as many ways of thinking about fast quantum algorithms as we do classical algorithms, right? So people have been thinking about classical algorithms for a long time. There are, many techniques that have been developed. I mean, going back even before we had digital computers, people were thinking about, processes for solving problems in a, following some prescribed sequence of steps. And, there are lots of algorithmic ideas that have been developed over, really centuries. And we've only been thinking about quantum computers for, a much shorter amount of time. And there's like very particular kinds of structures that you have to take advantage of to get some computational speed up from quantum mechanics. So the toolbox is, not as full. When we think about the toolbox for quantum computers, there are some techniques that show up again and again, certainly Fourier sampling, things like, unstructured, the Grover search algorithm and this framework of amplitude amplification. More generally, there's this idea of quantum analogs of random walks that's quite powerful and has led to a lot of quantum algorithms. And there are, some other techniques that have been developed, some of which are listed here. But, at the end of the day, the list is really not that long. So I think one thing that we can do to better understand the power of quantum computers, aside from just like finding more specific examples of quantum speedups, is really to develop tools that we can use to try to, systematically approach the development of quantum algorithms, within some kind of frameworks. And that's what we've tried to do in this work, to develop sort of a framework that we can use to design quantum algorithms of a particular kind. And as you'll see, it's really motivated by, a very well-known and well-studied classical technique, this idea of divide and conquer algorithms. And the framework that we've developed really allows you to kind of, in some ways, think classically about the design of the algorithm. So you can really design one of these quantum divide and conquer algorithms very much analogously to how you would design a classical divide and conquer algorithm. But, as long as it satisfies certain kinds of, properties, you can get a quantum mechanical speed up from doing the divide and conquer in this quantum way, despite sort of being able to think about it without kind of, having in mind, interference and superposition and these kinds of things when you're designing the algorithm. Okay, so let me start by talking a little bit about this, divide and conquer idea. And this is really a very basic technique in classical algorithms. Actually, so this semester I'm teaching a class at the University of Maryland, which is on algorithms. It's like the kind of second course that our CS majors take. And I'm actually right in the middle right now of teaching about divide and conquer algorithms. So I'm gonna go, this afternoon to teach my class, and I'm going to talk about this stuff. So this is like something that's really kind of bread and butter for classical algorithms. So the idea of this divide and conquer framework is that we have some problem we want to solve. We're going to divide it into subproblems in some way. And then what we're going to do is we're going to recursively solve those subproblems. So like the way we're going to solve those subproblems is by the algorithm that I'm now describing. And then we're going to somehow combine the solutions of these subproblems, maybe with some additional computation, in order to solve the full problem. Right. So to make this a little bit more concrete, let me describe kind of the classic example of a divide and conquer algorithm, which will also be the first thing that I'll talk about in my class, probably this afternoon, which is merge sort. So imagine we have some list that we want to sort. Okay, so here's some particular list of integers. Maybe we would like to sort this, and how can we sort it? So what we're going to do is the following. We're going to divide the list in half, right? So we have this list of length 8. We divide it into two lists of length 4. And then what we're going to do is we're going to recursively sort the left half and also the right half. Okay, so this is like the algorithm that we use here to, in this step is the algorithm that I'm describing now, right? But imagine we go through the whole recursion, we come back up, this is what the output is going to be, right? So we had this sublist and that got sorted, and this sublist and that got sorted, okay? And now what we have to do is we have to like merge the two lists, right? And the reason that merge sort is a fast algorithm, a fast sorting algorithm, is basically that this merging can be done really fast, right? So if I have these two lists that are in sorted order, right? They're not just like arbitrary lists; they've really been sorted. And what I want to do is produce the list that's the merge of these two, but in sorted order. I can do that by just taking like one linear path through the two lists. I just sort of like go through each of the lists, taking whichever number is the smallest, and putting that in my new sorted list, right? So that's just a linear time operation, linear time in the length of the input. And so we can write down a really simple recurrence that describes the cost of this procedure, right? The number of like comparisons we have to make to do the sorting. So what we do is we run 2 instances of the instance of half the size, right? That's kind of what we did here. And then we merge the 2 lists, and that takes linear time, right? So this is the recurrence. The cost of doing this for an instance of size n is twice the cost of doing it for an instance of size n over 2, plus something that's big O of n. And then you can solve that recurrence. You can use like the master theorem or whatever. You can, find some way of solving that recurrence, however you do it. The solution of that recurrence is that the cost is big O of n log n, right? So that's the complexity of merge sort, and that's, sort of the optimal complexity for a, for a comparison-based sorting algorithm. So that's really, kind of shows that this is actually an optimal algorithm for this problem, right? So yeah, that's kind of the general idea of divide and conquer, is kind of to have this kind of, recursive solution to the problem, which you can then, basically gives you some recurrence. And then by solving that recurrence, you can understand what is the complexity of the problem. All right, so the idea of this talk is to take this divide and conquer strategy and try to come up with quantum algorithms that have quantum speedup over kind of corresponding classical divide and conquer algorithms. Okay, so to kind of motivate this and why we might expect there to be some quantum speedups, I want to think about a simple example, not sorting. Actually, for sorting, we know you can have at most a constant factor quantum speedup. That's not a problem where we're going to expect to get quantum speedup. But let's look at a problem where there is some polynomial quantum speedup, which is the problem of computing the logical OR of a black box input. Okay, so we have an input, x1 through xn. We have the ability to make queries to those bits, and we want to compute basically, is there a 1 in the input, right? That's the logical OR function. Okay, so we know there's quadratic quantum speedup for this problem. So it's not sort of like a new challenge to come up with quantum algorithms for this problem, but let's sort of use this as a toy problem to try to see if we can think about it in a divide and conquer way. Okay, so if we want to kind of divide and conquer for this problem, we could say, well, let's divide the string x into the left half, so like x1 through xn over 2, and the right half, so like xn over 2 plus 1 up to xn. And then obviously the OR of x is just the OR of 2 bits, where one of them is the OR of the string on the left, and the other one is the OR of the string on the right. Okay. And now we can sort of like think about a recurrence for this. So first of all, if we would do this classically, obviously, like we know that there's the complexity of this problem is just n. You basically just have to evaluate all of the bits. But let's see that in a divide and conquer way. So the cost of the number of queries that we're going to make. So let's think about the cost now in terms of the number of queries to these bits. For this input of length n, is at most twice the cost of the input of length n over 2, right? So we evaluate this OR, recursively, and then we compute the OR of those 2 things, right? So we've got to do two of those evaluations. That's this factor of 2, right? So we have this recurrence for the query complexity. And so obviously the solution of this is that the cost is at most n, right? It's not a sort of interesting recurrence. That's what you get. But what we would like is that somehow, we could take this recurrence and we could say that in a quantum context, we have sort of an analogous but better recurrence that's going to give us a lower complexity. That's sort of the hope. And so you might think, maybe, I don't know, that maybe the quantum cost could be described by the same kind of a recurrence with a factor of the square root of 2. We know that there's a quadratic speedup for search. So if somehow, instead of paying a factor of 2 for, solving these 2 instances, you could pay only a factor of square root of 2, then what would you get? Well, then the quantum cost would be like something that scales like the square root of n, which is what we know is the query complexity of unstructured search. But this is completely unjustified and totally nonsensical. Because, for a variety of reasons. One thing is that, this square root of 2, the quantum query complexity of computing the OR, like computing this OR, it doesn't make sense to think about that as the square root of 2. We know that asymptotically, the query complexity of OR is like the square root of n, but that there's not a meaningful sense in which, the quantum query complexity of computing the OR of 2 things is the square root of 2, right? Square root of 2 is not even an integer. So what does it mean to somehow, evaluate, make square root of 2 queries? It's just not meaningful. Another issue is that if we sort of think about like computing this OR quantum mechanically, I mean, it's the bounded error quantum query complexity of OR that's square root of n. And if we're going to apply something recursively, a procedure that has bounded error, we have to worry about the way that the error could grow, right? And so, yeah, I mean, that's another sort of like wrinkle. You can't just imagine sort of like that you're plugging in these bounded error subroutines and just sort of ignore the error. You have to think about how those errors accumulate. Okay, but nevertheless, somehow we're going to, make sense of this recurrence, and we're going to show that we can have a recurrence like this that actually does characterize the quantum query complexity, right? So here's the kind of thing that we're going to be able to show. So, in our kind of generic application of divide and conquer, we're going to have some instance of size n. We're going to divide it into some number of instances, let's say a instances of size n over b. We don't necessarily have to have a equals b. I mean, these instances could overlap in some way, and they may in some applications of this framework. So we're going to solve a instances of size n over b, and then we're also going to, in general, have some auxiliary work, right? We didn't have that in the kind of unstructured search example. We did have it in merge sort. So, in general, we may have this kind of auxiliary cost where there's some additional computation we do to figure out how to combine the solutions of the subproblems. And so what we're going to do is we're going to sort of show that under some assumptions, like in some setting, if we have a classical recurrence like this, then we're going to be able to write down a corresponding quantum divide and conquer recurrence where we get to take the square root of a. So if this is like we're computing the OR of a things in the classical recurrence, there's going to be kind of a corresponding, square root of a in the quantum divide and conquer recurrence. And also this auxiliary work that we have to do to combine the solutions of the subproblems, is something that we can try to do with a quantum algorithm. And so if we have an algorithm whose quantum cost for solving this auxiliary problem is big O of some auxiliary quantum cost, then we're going to get a recurrence that looks like this. Okay, so that's kind of the where we're headed. We want to show that at least under some conditions we can somehow improve this recurrence to something like this, and we're going to see in some examples that this is going to give us polynomial quantum speedup for certain kinds of quantum query problems. Okay, any questions? Okay, so let me just make sure that so we're going to talk. So all of these results are going to be in this model of quantum query complexity. So let me just introduce a little bit this setting. I mean, this is kind of a powerful way of thinking about the relative power of classical and quantum computers, where we kind of characterize problems in terms of queries to a black box input. So in this model, the input is described by a black box. And you're not given the input explicitly. To learn anything about the input, you have to make queries to the black box. And then these queries are sort of the currency of the problem. So we're interested only in the number of queries that we need to make to solve the problem. So to learn some property of the black box input string. Like, for example, the string could be a bit string, and we want to know, is there a 1 in the string, right? That's the OR problem that we talked about already. But there's lots of problems that you can cast in this kind of a framework. And the sort of nice thing about this model is that unlike the kind of model where you're given an explicit input, it's quite feasible to prove lower bounds in this query model. So this allows us to get pretty crisp comparisons of the power of classical and quantum computers, because we can really pin down what is the complexity of solving some particular problem in this black box model. So in this kind of setting where we have a black box that characterizes the input, we can think about computation in various senses. We can talk about the deterministic classical query complexity, where we use a classical algorithm and it has to be right. We can think about the randomized query complexity, where we allow our classical algorithm to make random choices, and then we usually only demand that it succeed with constant probability, like let's say with probability 2/3. We can sometimes have faster algorithms if we give ourselves this additional resource of randomness, and we sort of only require kind of bounded error probability. And then we can think about the quantum model. And in the quantum setting, usually we think also about bounded error. So we can ask, how many queries do we need for a quantum algorithm that now can query the input in superposition. And again, it has to produce the correct answer with probability, success probability, say at least 2/3. There's nothing sacred about this 2/3. We could replace that with, kind of any other constant. We could make it, 99.9% if we want, and still, it would sort of only change the query complexity up to, like constant factors. Okay, so, yeah, I mean, the sort of example that we saw already was this problem of computing the logical OR of the bits. And this is a problem for which the deterministic and randomized query complexities are linear, but the quantum query complexity is like the square root of n. And this is in general kind of like the game that we want to play to try to understand comparisons between classical and quantum computation. Usually we're kind of most interested in separating the randomized and quantum query complexities. All right. So I want to introduce one other kind of idea related to quantum query complexity, which is going to be key to getting the kinds of quantum speedups that I want to tell you about from this quantum divide and conquer idea, which is something called the quantum adversary method. So the quantum adversary method is, it kind of originated as a way of proving lower bounds on quantum query complexity. It was sort of introduced by Andres and Binus in kind of the early days of quantum query complexity as a lower bound technique. But, it turned out later on through work by, Ben Reichard and some other people that actually this method is kind of always gives tight bounds if you consider a sort of like sufficiently general version of this quantum adversary method. So it's a lower bound method, but if you sort of look at the best lower bound you can prove by this technique, it actually gives you upper bounds. So the details of this model method are not going to be really important for what I want to talk about, but let me just introduce what the method is, just to sort of show you concretely what this method is. But the kind of specific formulation of the adversary method is not going to be so important for us. We're just going to use some of the sort of nice properties that it has. Okay, so in this quantum adversary method, we've got some problem which is characterized by some function from some set S to some other set T. So S is the set of inputs, right? So S is like a string over some alphabet sigma of length n, right? So n is like the input size. So, we're going to be given a black box input. We're given some particular string X, let's say, that comes from this set S. And then what we would like to do is we would like to compute the function f, right? We want to compute f of x given a black box, given black box access to this particular string over this alphabet sigma. And now the adversary quantity, so there's this adversary quantity that corresponds to any given problem that we might want to compute, as characterized by this function f. And that has a kind of sort of expression in terms of this optimization problem, which it turns out is a very nice kind of optimization problem called a semi-definite program that's sort of related to the fact that this lower bound technique actually turns out to be tight. That sort of tightness can be shown through this semi-definite programming duality. But anyway, this adversary quantity is defined as like a maximum over some adversary matrices. These are like matrices that characterize the these matrices are indexed by the possible inputs to the function, right? So they're entries of this matrix gamma x, y corresponding to pairs of inputs x and y. And somehow to give a good lower bound, you want to choose an adversary matrix that's going to make this quantity large. This quantity is the spectral norm of gamma divided by the largest of the spectral norms of any of these matrices, gamma I. Gamma I is a matrix you get by sort of zeroing out some of the entries of gamma in a way that's going to give you some information about sort of what you can learn when you query the ith bit of the input. So as I was saying, like the specific details of this expression are like really not important for this talk, but hopefully this gives you a flavor of like what this method is. It's basically, a method in which kind of there's some optimization problem, you vary over some matrix, and by choosing the best possible matrix, you get the best possible adversary lower bound on the query complexity of that function. And in fact, it turns out that this is tight. So like up to a constant factor, you can really understand what is the quantum query complexity of some function by solving this optimization problem. Okay, so yeah, this is this like kind of theorem that the quantum query complexity of computing any such function is big theta of this adversary quantity. So it really characterizes the quantum query complexity, so this is a really nice fact, but we're really going to rely on a kind of a further property of this quantum adversary method, which has to do with composition. So it turns out that this adversary quantity behaves very nicely under composition. If we sort of think about functions that we build out of other functions, then the adversary quantity for the for the composed function behaves very nicely in terms of the adversary quantities of the constituent functions. In particular, so if we have some function G that's the logical OR of two other functions, F1 and F2, then you can show that the adversary quantity of G sort of in quadrature is at most the sum of the adversary quantities of F1 and F2, right? So the square of the adversary quantity of G is at most the square of the adversary quantity of F1 plus the square of the adversary quantity of F2. And this actually generalizes to arbitrary, formulas that you build out of and OR gates. So this is a way of sort of understanding how the quantum query complexity of this composed function relates to the quantum query complexity of the constituent functions. I mean, I say quantum query complexity because we know that the adversary quantity of a function is big theta of its quantum query complexity, right? And so this is going to be useful in this divide and conquer framework. This is going to be a way that we can sort of like have some quantity that doesn't have to be an integer that really relates to the quantum query complexity, right? The thing we're going to look at is going to be not sort of directly the quantum query complexity, but rather the adversary quantity of some function. And this is what's going to sort of allow us to make sense out of this, solving square root of 2 subproblems. We're also, for some of these results, going to use another kind of composition that I think maybe hadn't been stated so explicitly before our work, although it's a pretty straightforward consequence of kind of behavior of the adversary method. And the way this works is follows. So suppose you have some function you want to compute, and the way that you compute that function is first you compute some function f of the input. That tells you which function g you want to compute. So it's like an index of which function g you're going to compute, and then you compute that function g, of the input x. Right. So what you can show is that the adversary quantity of a function that's composed in this way, where you basically you compute one function to figure out which function you're going to compute of the input. That adversary quantity of h is at most big O of the adversary quantity of f, the function that tells you which of the g's to compute, plus the largest of the complexities of the g's. Right. So this is a case where, here you can imagine there's effectively some square root, right? Like if F1 and F2 have the same cost, then what this shows is that the adversary quantity of G is at most the square root of 2 times the adversary quantity of, the function f that you're computing. In this case, we're not sort of getting any square roots on the costs. We're not going to get quantum speedup from these kinds of recurrences. This is basically describing a strategy where the way you're going to compute h is first you're going to compute f, and then you're going to compute the corresponding g. So there's not quantum speedup from this, but what we're going to the way we use this in some examples is sort of to combine it with other things like this that do give us quantum speedup in order to get some speedup overall, but where this composition is going to be sort of essential for the overall thing to go through, right? It's going to be kind of this framework that we have introduced kind of relies on the ability to go back and forth between thinking about things in kind of quantum query complexity language and adversary language. And this composition rule is going to allow us to do that in a way that's going to provide for quantum speedups when we combine various parts of the computation. Okay, so now I'm finally in a kind of a position to tell you about how this quantum divide and conquer framework works. So, if we have some function that we can compute as an and/or formula of a bunch of constituent functions, and then there's also some auxiliary work that we do to put the solutions of those subproblems together, then you can show that the square of the adversary quantity of this function f is at most the sum of the squares of the adversary quantities of the fi's plus the square of the adversary quantity of this thing, which is big O of the quantum query complexity of that thing. Right, so you can imagine that if you design a quantum algorithm to solve this auxiliary function, then whatever the query complexity of that is, the adversary quantity is big O of that, and sort of then applying this kind of and/or composition, kind of gives this this rule for the adversary quantity of the composed function. Similarly, if we've got some function that's computed by first, evaluating some auxiliary function and then computing some function gs that's determined by value of that auxiliary function, then we can use this switch case composition to get this kind of bound. So, Yeah, I mean, what these strategies do, as I was saying before, is that they somehow combine the quantum adversary method, which is, sort of something that we can more tightly characterize than the quantum query complexity, right? The quantum query complexity, typically we only characterize up to a multiplicative constant factor. But the, adversary quantity, we can really sort of understand very precisely, what its value is. So when we have sort of a term in this recurrence where like the coefficient really matters, then we sort of want to be able to get a very tight value for that coefficient, and so for that we kind of want to stay in the adversary method. And we want to combine this with sort of the world of quantum algorithms, where it's kind of easier to think about designing things, right? So for like solving these auxiliary problems, we would rather just maybe design a quantum algorithm. Maybe we don't care about the constant in the big O. And if we don't, that's going to sort of free us up to just think about things in the quantum algorithms world. And so you'll see in some explicit examples that I'm going to do in a moment, this is all going to become more concrete. And you'll see what I mean by sort of combining, sort of designing a quantum algorithm with some other part where sort of using the fact that the adversary quantity composes very nicely, we're going to get sort of, a good coefficient that's going to allow for this kind of quantum speedup. I mean, so I should emphasize probably that this idea of sort of using adversary composition to get quantum speedups is definitely not a new thing. I mean, it's been applied in kind of other contexts, but usually, when this adversary composition has been applied, everything is sort of like stayed in the adversary world, and only at the end of the day do you say, okay, we can use this bound that we get on the adversary quantity to then give a quantum query algorithm. So this framework that we have introduced, where we're sort of divide and conquering, we're like kind of at every layer of the recursion, kind of going back and forth between the adversary quantity and the quantum query complexity, and this sort of allows us to get new kinds of quantum speedups. Okay. I mean, it's also possible that we could, get other kinds of ways of dividing and conquering using other adversary composition rules besides the ones that I've mentioned here. I mean, there are other ways, other nice ways that the adversary quantity composes that we haven't yet applied in this framework, and I think that would be maybe an interesting thing to think about. Okay. Great. So that's like the general framework. So now what I would like to do is maybe describe some applications. So first, just an overview of like what are the applications of this framework that we know. So first of all, there are some problems for which, there were good upper bounds on the quantum query complexity that were known before, but we can sort of reprove them using this framework. And the analysis is, this is always like in the eye of the beholder, I suppose, but the analysis is arguably a bit simpler, once kind of this framework is established. And, the upper bounds are, in some cases improved, like with respect to the log factors. So one such problem is a problem related to quantum query complexity of recognizing regular languages. In particular, you can think about this problem where you have an alphabet of size 3. So you have symbols 0, 1, and 2, and you want to know if some given string, which is provided to you by a black box, some string over this alphabet contains a substring that looks like this. So a 2 followed by some number of zeros followed by a 2. This is this may seem like a little arbitrary, but there's this nice paper of Aronson, Greer, and Schaefer where they developed this kind of quantum query complexity trichotomy theorem for regular languages, where they show that if you want to recognize kind of general regular languages, its quantum query complexity will be one of 3 possibilities. And sort of understanding the quantum query complexity of this particular language was sort of key to establishing that result. So we're able to reprove that result in a pretty simple way and improve the log factors in the quantum query complexity. And there's also this paper on some quantum algorithms for various kinds of string problems by Akmal and Jin, where they consider a lot of different problems. And for some of these kind of string minimality problems that they consider, at least for decision versions of those problems, we're able to give this kind of simpler analysis with better log factors. So yeah, maybe the sort of like details of these problems are not so important, but there's some problems of these kinds for which we can give for the decision versions of the problem, we can give this kind of simpler and slightly tighter analysis. Okay. So those are kind of like kind of reproofs of previous results, but we also gave some quantum algorithms for problems where, there was where we were sort of the first to give these upper bounds on these problems, and for which I would say there were not, previously any kind of non-trivial quantum improvements. There are sort of quantum improvements that follow very straightforwardly from known quantum techniques, but we really sort of push beyond those by developing these this new framework. So, and these are like some kind of parameterized versions of the longest increasing subsequence and longest common subsequence problem. So these are like problems that are well-known, well-studied problems in kind of a classical context. So the first problem is, we're given some black box string X over some kind of ordered alphabet, and we want to know, does it have an increasing subsequence of length K? And we show that the quantum query complexity of that problem is like the square root of n, if the length of the input X is n. And if we're given two strings, X and Y, each of length n, and we want to know, do they have a common subsequence of length, at least K, then we show that the quantum query complexity of that problem is big O of n to the 2/3. So I would like to explain how we can get some of these upper bounds using our framework. And we're not going to have time to go through all of them, but I'd like to give you at least some of a flavor for how you can get some of these improvements, using our framework. Maybe this is a good point to pause for questions if there are any. Okay, if not, maybe the examples will, perhaps help to make, some of these ideas more concrete. Okay, so let me start with this regular language problem. As I said, this is sort of like a reproof of a previous result, but this is probably the kind of one of the simplest applications of this framework that I think shows some of the main ideas. Okay, so here's the problem. So we have an alphabet with 3 symbols. So let's say 0, 1, and 2. And the problem that we're interested in is we're given a string over this alphabet, and we want to know, does that string contain a 2 followed by some number of zeros followed by a 2, right? So in terms of kind of regular expressions, right, we want to know, is X in sigma star 2, 0 star 2, sigma star, right? Does our string have this kind of substring in it? And so we're going to think about how to divide and conquer for this problem, and there's like a very natural way of trying to divide and conquer to try to identify such a string within our string. So you can see that this 2, 0 star 2 will be inside X somewhere if one of 3 things happens, right? So we're gonna divide and conquer in the kind of simplest possible way, which is we think about dividing up X into the left half and the right half, right? So the first n over 2 characters of X followed by the second n over 2 characters of X. And one possibility is that this substring is entirely within the left half. Another possibility is that it's entirely within the right half. And then the other possibility is that it bridges the 2 halves, right? And for it to bridge the 2 halves, what has to happen is that the string on the left has to end in a 2 followed by some number of zeros. And the string on the right has to start with some number of zeros followed by a 2, right? So this covers like all the ways that this substring could appear within X, right? So now these first 2 instances, these are obviously just instances of this given problem of half the size, right? This is exactly what we do in divide and conquer. We're going to solve exactly the problem that we care about on an instance that's smaller, in this case of half the size, like we had in merge sort, right? But now the question is, what about this, right? What's the cost of solving this problem? And now the point is that just we can develop a quantum algorithm for this auxiliary problem that does not have to make too many queries. Okay, how do we do that? You can show, it's not so hard to see, that just using Grover search, you can solve this problem in times square root of n. I mean, I say time, but I really mean query complexity, right? We're always kind of counting queries. I mean, you really can't do it in this amount of time, but what matters for this analysis is the query complexity, right? So the way we're going to do this is we're going to search for the last 2 in the left half of the string and the first 2 in the right half of the string. And you can show that you can really get, I mean, there's maybe some log factors here, but up to log factors, you can really find not just, whether there's a 2 in the left half, but where is the last 2 in the left half and where's the first 2 in the right half. You can do that in time like square root of n. And then we want to know, is the string between the last two on the left and the first two on the right, is that all zeros, right? If it is, then, you have this kind of situation, and otherwise you don't, right? So, so what we can do to figure that out is we can search for a non-zero in the string between those two twos, right? And that's something also that we can do in like times square root of n. Right. So we had to make basically like three Grover searches, to understand this stuff that's highlighted in yellow. Right. So that then gives us a recurrence for this problem, right? For let's think about it as a recurrence for the adversary quantity for this problem. And if we use this kind of composition rule that I described before, what we see is that the adversary quantity for this problem for an instance of size n, if we square it, is at most twice the adversary quantity for an instance of half the size squared, right? So here you see that if we would sort of take square roots everywhere, we have the square root of 2 that we were looking for. And then what's the cost of this auxiliary problem? Well, it's like big O of square root of n, because we just did 3 Grover searches. But again, we're adding everything up, kind of in quadrature. So we have big O of square root of n squared, right? And if you solve this recurrence just using like, the master theorem or, however you like, what you find is that the adversary quantity for this problem is like the square root of n log n. Right. And so the adversary quantity is big theta of the query complexity. So this is really what the query complexity is, right? This really shows us that we can solve this, regular language recognition problem in time, basically like square root of n up to this square root of log n, additional overhead. Right. So this has like slightly fewer log factors than the log factors weren't even like worked out explicitly in this paper, but if you would work them out, I think they would be a little bit more than the square root of log n. And also the analysis is arguably simpler than what you'll find in the kind of original regular language trichotomy paper, right? And so let me emphasize again that really, hopefully you can see now what I meant by kind of going back and forth between the adversary method and kind of the quantum query complexity world, right? Sort of the way we're thinking about analyzing this yellow thing is in terms of quantum query complexity, right? We're actually giving a quantum algorithm for solving this problem, and then just using the fact that the adversary quantity is big theta of that, right? So, so this analysis is done in kind of the quantum query complexity world. The recurrence is really done in sort of the adversary world. And so if you think about, actually solving this recurrence, you're kind of going back and forth at every level between a quantum query algorithm for the, solving this subproblem and sort of like thinking in a sort of adversary way to get this constant. And so for this to be the square root of n, it's really crucial that this is a 2, right? If this would be like a 3 or something, then we would not get this tight bound, right? It's kind of crucial to kind of use the adversary bound to really get this coefficient to be 2. Here we don't care about the constant; it's fine as long as it's just something that's big O of the square root of n, and it's still going to give rise to the same solution. Okay, so that's maybe the kind of the simplest application of our framework. Let me next mention this increasing subsequence problem to sort of like give you, at least one of the examples of a problem where there's something a bit more non-trivial going on. In particular, like we're getting a quantum speedup where one that wasn't previously known. Okay, so this problem has to do with subsequences. By a subsequence of a string, I mean something that you get by taking a subset of the characters without changing their order, but they don't have to be consecutive, right? So like if they had to be consecutive, that's what we call a substring, but here they don't have to be consecutive. So that's what we call a subsequence. And there's a very well-known problem in kind of, classical computer science, which is the longest increasing subsequence problem. So we're given some string of length n over some alphabet sigma. There's some like total order on the elements of that set. And we want to know, we want to find a longest increasing subsequence of x, right? So for example, if we have this subsequence or this sequence, 8, 6, 7, 5, 3, 0, 9, then the longest increasing subsequence is 6, 7, 9. In this case, maybe it's probably unique. It doesn't have to be unique in general, but in this case, I think maybe it is. All right, so this is a natural problem, which we could try to think about with quantum computers. But unfortunately, if we just think about this kind of like unconstrained longest increasing subsequence problem, the quantum query complexity is just big theta of n. Like you just need to know the whole string to be able to figure out what is a longest increasing subsequence. So that's, I guess, kind of a bummer, but it's sort of not hard to show that somehow it's just not possible for this problem to get any quantum speedup. So in order to have, something interesting to talk about, we're going to look at this parameterized version of the problem where we fix some, parameter k. So if k is some positive integer, and we ask, is there an increasing subsequence of the input x of length k? Right. So is there an increasing subsequence of length 2, or is there an increasing subsequence of length 10, or whatever's your favorite number k? Okay. So now, classically, if k is at least 2, then the randomized query complexity of this increasing subsequence problem, parameterized by k, is already big theta of n, right? You already have to know the whole input string just to know if there's an increasing subsequence of length 2, right? I mean, increasing subsequence of length 1, like that's not an interesting question. Like, there's always an increasing subsequence of length 1, because you can just take any single character and that's an increasing subsequence. But if you want to know, is there an increasing subsequence of length 2, like that's already hard, as hard as it could be for classical computers. But on the other hand, quantum mechanically, of k equals 2, it's easy to see that this 2 increasing subsequence problem is basically just equivalent to unstructured search. You're just looking to see, are there 2 characters where the second one, occurs after the first one, and the second one is, greater than the first one. And you can basically solve that by solving an unstructured search problem. You can give sort of upper and lower bounds using the known complexity of unstructured search. So what about this problem for larger values of k? Well, it's very easy to see that for any fixed value of k, you can apply this algorithm of Mbinus for he developed it for the k distinctness problem, but it kind of applies more generally to problems that just depend on some subset of k items. And the sort of query complexity of this algorithm is like n to the k over k plus 1. So for any fixed k, if you're trying to solve this k increasing subsequence problem for a particular value of k, you can give this quantum query complexity just using standard quantum algorithms out of the box. Really, kind of like it's just really a straightforward observation. But now the question is, can we do better, right? I mean, like for 2is, you can get square root of n. For kis, for very large k, this is going to become close to linear in n, which is really not much improvement at all over kind of the trivial algorithm. So, if k is 1,000, this is like, almost like just the trivial algorithm. So, what can you do? And so what we're going to show using this framework is that actually you can get this complexity to really be just like the square root of n for any constant k, even for k equals 1,000 or for k equals 1,000,000, you can get square root of n. Okay, so let me just like briefly explain how this works. So, so this is what we show, that the query complexity is like square root of n up to some log factor that grows with k. But as long as k is a constant, this is just some constant, power of log n. And so here's how the algorithm works. So we're again going to just divide into 2 parts, a left part and a right part. And the string x is going to contain an increasing subsequence of length k if and only if there's one on the left, there's one on the right, or we can find one that crosses from the left to the right. And there's a bunch of different ways that could happen. You could have I elements on the left and k minus I elements on the right for any value of I between, 1 and k minus 1. And the kind of observation here is that you can check this condition in yellow by basically solving some subproblems that are increasing subsequence problems, but for increasing subsequence problems with smaller values of k. Right, so like you have to look at sort of whether there's an I increasing subsequence on the left and a k minus I increasing subsequence on the right. And here I is only going to have to run from like 1 up through k minus 1. So these are always going to be increasing subsequence problems of smaller size. And so you can show that you can do this using computations of this increasing subsequence problem for smaller values of here j. And the number of them that you need to do is like, logarithmic. Combine that together with sort of Grover search. Yeah, I mean, if you sort of like understand exactly what are the things you need to combine here, then you get a recurrence for the adversary quantity that looks like this. So crucially, number of instances of the problem of the same size, where it's a increasing subsequence of length k, is only 2, right? There's the one on the left and there's the one on the right. And then there's some logarithmic number of instances of smaller size that contribute to this term. And if you solve this recurrence, what you find is this solution, right? So somehow the fact that these are all smaller instances, let you get sort of, have this term dominate and have the query complexity be only square root of n up to these log factors that, do grow and grow as k gets larger and larger. But for any constant k, the query complexity is, up to log factors, just the square root of n. Okay, so that's, an example of a kind of, non-trivial, sort of like a new quantum query complexity upper bound that we got from this method. Another, example that we give is for this parameterized version of the longest common subsequence problem. And I think in light of the time, maybe I won't try to sort of go through any of the details of this problem. But, we look at sort of like a parameterized version of this problem where, again, we ask, is there a common subsequence of length k? And, this is, again, a problem for which the classical query complexity is sort of like maximal already for small values of k. And there's sort of, a similar situation that for larger values of k, previous algorithms give you something that's, not great, that sort of goes close to linear for large values of k. And the question is, again, can we do better? And sort of what we show is that you really can do better. You can get a quantum algorithm whose complexity is like big O of n to the 2/3, which is basically optimal, sort of up to this up to this log factor. So I'm not going to go through the details of this because I think there's not time, but I'll just say that one thing that's maybe surprising about this, which is something you don't usually see in divide and conquer algorithms, is that to get this, it's not sufficient to divide the problem into 2 parts. You have to divide the problem into 7 parts. Which is a little, kind of unexpected. If you would divide it up into 8 parts, like it wouldn't get any better. Like somehow dividing it up into 7 is sort of where you have to go to get the optimal algorithm. But somehow, yeah, in order to get the recurrence to solve to this optimal n to the 2/3, to have sort of the the term that leads to this n to the 2/3 be dominating, somehow it's essential to divide things up into 7 parts. So that happens for a reason that I could explain if I had more time, but maybe I won't, just so that we're not letting things drag on too long. All right, so maybe that's a good point to kind of stop and just sort of summarize what we know. So we introduced in this work this divide and conquer framework for quantum algorithms, which really, hopefully you've seen through these examples, lets you kind of use classical reasoning about the way you divide your problem up into subproblems and really think in the way you would think about, doing a classical, divide and conquer algorithm. But we get a quantum speedup from the way we're allowed to combine things in kind of a quantum world, right? So we can use quantum subroutines and we can combine the solutions of subproblems quantum mechanically. And that sometimes, leads to speedups that we, over what we could do if we would do the analogous thing classically. And so, using this technique, we got these, simpler algorithms or simpler analysis of the quantum query complexity upper bounds for some problems that had been studied before. And we gave these, first non-trivial algorithms for these parameterized versions of increasing subsequence and common subsequence. So that's sort of like what we've done with this framework so far. And I think there's lots of things one could potentially think about in the future. One thing that I think is a limitation of our method that it would be nice to overcome, and I was mentioning this in some of the discussion we had just before the talk, is that our method is really kind of only suitable for solving decision problems. It's really kind of this is, I think, kind of a limitation of the way that this adversary composition can be applied. It's kind of crucial that we're only solving decision problems along the way as we solve subproblems and then combine them together. If we would need to really like search for something and then try to use the result of that in the adversary composition, that's something that we don't know how to do. And in particular, I think a nice kind of test case for understanding whether you can apply this method to search problems is to think about the problem of finding the minimum, right? So if you have some, list of numbers and you want to find the smallest number in that list, okay, we know you can do that in quantum query complexity like square root of n. You can get the Grover speedup for that problem, but we don't know how to do it in a divide and conquer way. I mean, it's sort of like at an intuitive level, it's obvious. Like you find the smallest number on the left, you find the smallest number on the right, and then you compute which of those two things is smaller. And if you could get a square root of 2 speed up for that, figuring out which two things is smaller, then you would have this kind of a result. But we don't have kind of an adversary composition result that allows us to do that. So yeah, understanding like if that problem can be solved with divide and conquer, and more generally, if you can kind of extend this framework to handle search problems is, I think, an interesting thing to think about. I also mentioned that we only use these two combining functions in our recurrences for this divide and conquer framework. One was this kind of and/or composition, and the other was this switch case composition. But there are lots of other things that are known, like if you want to compute, let's say, the majority of 3 bits, there's some quantum speedup you can get for that at the level of the way the adversary method behaves. There's a bunch of other functions for which nice adversary composition properties are known, and maybe some of them have applications to quantum query problems using divide and conquer algorithms. And finally, these problems that I mentioned, these are all problems for which we get polynomial speedup using quantum algorithms as compared with classical ones. But I think there's no reason in principle why we couldn't have larger than quadratic speedups using this method, maybe even exponential speedups. There are examples of superpolynomial quantum speedups that have been shown using adversary composition, but not in this kind of divide and conquer way that I've described in this talk. So it would be, I think, really exciting if we could have more than quadratic and maybe even more than polynomial speedups using this framework. Okay, great. So I think that's all I wanted to say. So maybe I'll stop there, and if there are questions, I would be happy to answer any more questions.
Well, thank you so much, Andrew, for a beautiful introduction to quantum divide and conquer. I'm going to stop here screen sharing and hopefully put a gallery mode so we can see each other. I think there'll be many questions and discussions. I'll look forward to that. Maybe I'd start out by asking a question, because I'm not an expert on this at all. And I wonder, when you mentioned dividing into more than 2 subsets, whether in classical problems, this is something that's done and important. And that's one question. And a second question had to do with whether you have searches which involve higher dimensional geometry, and whether there are cases in which different types of dividing in higher dimensions and the geometry could help.
Yeah, okay, thanks. Yeah, those are interesting questions. Let's see. So I think it's quite rare that somehow you ever want to divide into more than 2 parts in algorithms. I don't know of an example offhand, where sort of in a classical context you do some divide and conquer thing and you have to divide into more than 2 parts. There probably is some example that maybe I just don't know of offhand, but I think it's kind of a rare thing, and it's in our analysis for this common subsequence problem, I guess I don't know, because we're getting speed up for a term quantumly where we wouldn't be able to classically, it sort of like opens the door to having this possibility of getting more speed up, but only having more parts. So there is something kind of going on there that happens quantumly, but not classically for this particular problem. But, the sort of space of the things you could do with divide and conquer in a classical setting is very large. So, yeah, while I can't point to a particular example, I wouldn't be surprised if, there is one out there somewhere where it makes sense to divide into more than 2 parts, but I think it's kind of rare. So your other question was about higher dimensional spaces. I mean, all of the problems that we have examples of, that I mentioned in the talk, they're all kind of string problems. And so they're I don't know. And at some level, they're kind of one-dimensional in the sense that, the strings have some order. That order is relevant to the problem. You divide things by dividing in the middle. So there's sort of, they're not really geometric problems, but to the extent that you can think about them that way, they're sort of very low-dimensional problems. There are other problems where you can think about sort of really geometric problems where you can think about applying divide and conquer. And actually, one of them is a problem I'm going to do in my algorithms class, which is a kind of basic computational geometry problem. So you have points in space, and so you're given n points in space, and you want to find the closest pair of points, right? So there's a kind of a trivial way of finding what's the closest pair of points by just considering all pairs. But that's going to take quadratic time in the number of points, and you can get sort of an n log n algorithm, at least in 2 dimensions, and probably you can extend it higher dimensional cases, by some kind of recursive subdivision into sort of halves of the space, and sort of looking for the closest pair of points on the left, the closest pair of points on the right, and then the closest pair that kind of crosses the 2 parts. And so you can get a kind of an improvement classically using divide and conquer over the kind of brute force approach. There is actually quantum work on that problem, and you can get some improvement for that problem, although it doesn't use this divide and conquer framework, the quantum divide and conquer. It does something different. I forget exactly how that algorithm works, but there's a nice paper about that. But anyway, that's at least an example of a problem where in the classical setting, you're doing some divide and conquer thing to sort of solve some, really geometric problem. Yeah, I mean, I don't, have other examples offhand, but I mean, I do think it's an interesting thing certainly to think about.
Thank you. So I'm sure other people have questions, or maybe I see Shun is here. Do you have any comments about connections with quantum supremacy?
Oh, sorry. I'm using iPad. Yeah. I don't know, because it's query complexity, so maybe it's not too near term.
Right, for sure. Yes, I agree with that.
Yeah, but I'm curious about whether what's your opinion about the potential of super polynomial speedup? Do you think it's possible to have exponential speedup using this method?
Yeah, I mean, I think it's an interesting question. I'm not really sure. I mean, so I mentioned that there are examples of super polynomial speedup using adversary composition, right? So there's this nice work that Shelby Kimmel did, where she sort of constructed a sort of kind of formula evaluation problem. And we know that there are these, quantum speedups for formula evaluation problems, but by kind of putting a promise on the kind of input that you can have to the formula, you can sort of make the problem, actually have a big gap, actually have a super polynomial gap between the quantum and classical query complexity. But the quantum algorithm for that problem really, is really kind of just using this adversary composition, kind of staying within the adversary world. So I guess, I mean, a question could be, could you come up with a problem, even a toy problem, where somehow you would have to do the kinds of things that we do, in this work that I described to realize that super polynomial speedup. So, maybe you could do that. I mean, I guess a thing to try would be to think about some of the kinds of problems that we have speedups for, but try to impose a promise, try to sort of carve out, a promise on the, the possible inputs to, a longest increasing subsequence problem or something like that, or a regular language kind of problem. You have some promise on the string that somehow allows you to, sort of accelerate the things quantumly relative to what you can do classically. I mean, I don't have a really concrete suggestion, or I would be telling you about that result instead of, or maybe in addition to the stuff that I told you about. But I think it's definitely worth thinking about.
Do you think the most, non-trivial part is basically how to combine 2 subproblems together? Is this step the most non-trivial part?
I think it's like finding a problem that would have the structure. I mean, I think we understand pretty well how these things, how to compose the algorithms. I think if we had, I mean, I think if we had the problem, we would know how to analyze it because we have the tool, right? yeah, I think that the challenge would be to sort of like, either design a problem, maybe a very artificial problem for something like where something like this happens, which I think would already be interesting. Of course, even better would be to like, identify some really natural problem that you really want to solve for which something like this happens. But yeah, that to me is it seems like more a challenge of like finding the right question, than figuring out how to analyze the algorithm for it.
Okay, yeah, thank you.
Sure.
So are there any other comments or questions?
Seems like maybe not, but thanks for the opportunity to talk about this work.
So I'd like to thank you again, Andrew, for a really beautiful talk. And we look forward to how this field develops. It's wonderful.
Yeah, thanks
So
very much. If anyone has any other questions offline, I'm happy to take them. Yeah, thanks a lot.
Bye-bye.
Bye.